Greetings, math friends. I know I'm not first to take a look at this, and I don't know if anyone will follow me after this, but I want to take another look at this integral, which has showed up in various places online as the free Wi-Fi password integral. Sometimes it's attributed to China. I've seen a different version that's attributed to India, and there are slight variations that occasionally show up. One of them being whether the differential is inside the square root or outside the square root. A lot of times when people have attempted this, if they've chosen the version where the differential is in the square root, they immediately move it outside, either without comment or with comment that it probably shouldn't have been there. It's a typo. I talked to a couple other mathematicians about ignoring this or thoughts about possibly approaching this from a fractional differential or integral perspective. I talked to my best friend, and he kind of put me on the idea that it's slightly related to Dirac's Nobel Prize winning work, where he had a differential operator in a square root that he had to resolve, and he did that using a couple other mathematical techniques to be able to resolve that. This one's less difficult maybe as what Dirac was looking at, and a couple of us have seen this as something that perhaps we need to approach as either a Riemann-Stieltjes integration or as just looking at the Riemann sum. The one modification that I'm going to make to this statement is I'm going to assume that we need parentheses here, and really parentheses that delineate that the input of cosine is just the x over 2. And that's the only modification that I'm going to make. And from there, I want to do this integration with the assumption that we have the square root of the differential here. Now, one of the mathematicians that I talked to immediately seemed to see that the solution of this was divergent, but I wanted to follow that process and watch it happen. So that's what I'm going to do here. Most people note immediately that some of the stuff that we have going on here is an odd symmetric equation, and that I'm going to use some of that thought process as well. Firstly, I'm going to separate this integral into two separate integrals. Because we have the addition here, this distributes into this set of parentheses, causing this piece to be multiplied by this first piece, and then multiplied by the half. I separate on the plus. And I'm also, due to the properties of square roots, going to split this product into two separate square roots. Over here I have the half that has passed through the integrand, and then I have just the square root of 4 minus x squared times the square root of dx. I'm going to spend some time focusing on this left-hand side first and dealing with this piece here. The first three, essentially these are functions all on their own that are being multiplied together. That's really one function for the process of integration. But this product of functions gives us an odd function. Pulling this piece out as a function, if we would put negative x into this, the only part that really retains the negative is the x cubed. The negative input in the cosine is the same as the positive input of the cosine because it is an even function on its own. This likewise would be an even function on its own and would not retain the negative. The x cubed is an odd function on its own and retains the negative. And essentially the product of an odd function and an even symmetric function gives you an odd symmetric function. We see the negative retained here. We could pull that negative out and see that f of x would be the same as taking a -1 and multiplying it times f of x to get this. So that's our demonstration that we have an odd symmetric function. That means essentially, since we're integrating across an even interval that's symmetric about the origin, anything that we pick up on the left-hand side is eliminated on the right-hand side. The reason for that is because part of this is going to be below the x-axis. Part of it's going to be above the x-axis due to this being symmetric about the origin by rotation. So now that we've established that, we're anticipating that as we integrate this piece is going to go to 0, and then we have to deal with the square root of the differential. I've already said we're going to take this perspective from a Riemann sum, so we need to identify some things from a Riemann sum perspective. So you can look at a calculus book like Edwards and Penny or some other text. I started learning with Edwards and Penny back as an undergrad in Calc 1. You can see that x sub I is going to be defined by the linear equation a plus I times delta x, and delta x is going to be defined as b minus a divided by n. So this is establishing your interval, and then each interval break. So in our case, x sub I is going to be -2 plus 4i over n. So we're going to plug this in to this function. So I've just written this here as f of this x sub I value, and then the square root of dx is going to be 4 over n. So you take your interval and divide by n, and we are integrating from -2 to 2. So we're going to take the limit as the partition approaches 0 of the sum of this. On the right-hand side, I also did a little simplification, but we're still mostly ignoring the right-hand side for now. I want to focus on what's going on this left-hand side before we get to the right-hand side. Over on the right-hand side, I just eliminated the 1/2 out front by, again, using this interval being symmetric about the origin. I rewrote this as an integration from 0 to 2 and pulled that 2 out to eliminate the 1/2. I moved this up a little bit and erased some of the other work so I have room here for you to see. What surprised me about this, I mentioned that this is going to 0 while this is attempting to go to infinity. Essentially, this goes to 0 before this hits infinity. And that threw me off. If we pull this through the sigma, the summation notation here, these are all continuous functions, and we look at this limit as n is going to infinity, we know that this is going to 0. So we're going to have the product of 0 times this value here, and 0 times another real number is going to be 0. Remember, this is a limit that we're approaching here. So we're going to have 0 times this is 0, so we have the limit as n approaches infinity of something that is identically 0 because of this product. So this just goes to 0. That surprised me. I expected this part to really be the divergent part. But we see that, again, we're ignoring, I've been ignoring the right-hand side, but it still exists here. This is the limit as n approaches infinity of 0 plus this part. Okay, so this is going to be 0 plus this. So starting on the left-hand side, we see that since this goes to 0 and we're adding it to this, it's really the right-hand side that we need to focus on to find out what this integral actually does, with the assumption that this is the square root of dx here being multiplied by this difference of squares. So here is where the real action is going to take place. Since I changed my interval of integration, we are going to have to establish a new x sub 1 and delta x. So x sub 1 is going to be 0 plus 2i over 1 because the difference here is now a unit of 2. So we're going to plug that into here again, looking at the Riemann sum to evaluate this. And at this point, we've got to do a little bit of algebra for a while to get this to a place where we can make a substitution, which Jim and I actually suggested to me to simplify the work a little bit. But I got to get to that point where I can make that nice substitution. We can square the values in here and get 4i squared over n squared. We've squared this. I see I've got a common 4 in here. That's a square number. I can factor a 4 out here. The square root of 4 is 2. So I'm going to pull a 2 out. I'm able to, again, had a mistake there. I'm able to, again, pull this through because this is a continuous function. So factoring the 4 out and then taking the square root, I've got this 2 here. So this ends up being the type of form that I'm looking for. I need one more piece to this to meet the lemma, essentially, that the AI suggested that I use to simplify the calculation. I'm going to focus on a little bit of algebra right here. So I'm going to split that, do the square root of numerator and denominator, and then I'm going to rationalize the denominator here. The 1 over n that we gain by rationalizing the denominator here, I'm going to pass through the sigma, the summation notation here, to have this 1 over n here as a multiplier on this square root function. It leaves me with an extra square root n over here, all in line. And now we're going to focus on this. We have a lemma that's going to allow me to do a substitution here. The lemma that the AI pointed out to me that would be useful is to observe that if we integrate from 0 to 1, the square root of 1 minus x squared dx, the integral we get is going to be 1 over n. The difference is 1 over n. So we can make these substitutions, and we can have that the Riemann sum of this is going to be from 1 to n of 1 minus 1 over n squared times 1 over n. And we use that fact to substitute in to the main integration that we're doing to just try to make this a little faster. Part of that is, once we know that we can take this and substitute in this, we can integrate this. So integrating this without using Riemannian sums, we have an antiderivative here that we can evaluate from 0 to 1, and then substituting in 0 and 1, we get that we have 1/2 minus pi halves, and that is equal to pi fourths. And we're going to use this substitution in as well once we identify that this is available to us. And this is going to give me that this is O equivalent to the limit as n approaches infinity of 2 times square root of 2 times square root of n times pi fourths. Evaluating this limit, the only n I have left here is this one. This is going to infinity, so this whole product diverges to infinity. So we had this, we split into two integrals. The first one went to 0, and that's added to infinity. The sum of 0 plus infinity is going to give us infinity. So this overall diverges to positive infinity. So if this is a Wi-Fi password, if we ignore the fact that they told us they wanted the first 10 digits of the evaluation here, you could have this to represent a Wi-Fi password of diverges, divergent, infinity. There are a variety of things that we could actually have words as our password and not a numerical representation. It still would leave some things up in the air. The fact that they had the square root of the derivative in some of the examples, several people believe that that was really a typo that showed up at some point. I have seen versions where the dx is outside of that completely, and then there are people that are dealing with this inside. Hopefully this has been interesting to you. It's been a question that's been on my mind for a few years, and I'm finally now putting this video together. Cheerful Calculations.